There's a few things we still need to go over in terms of topic one. I have a food web here. You did a food web for your summer assignment, and one of the things that wasn't necessarily clear to everybody before the summer assignment is the direction of the arrow matters. The direction of the arrow indicates the direction that energy and or matter flow. So the energy starts with the producers, and this is called the first trophic level. Trophic meaning energy. So the first trophic level is where the producers are. Then the primary consumers are said to be the second trophic level. Secondary consumers are the third trophic level. And the tertiary consumers are the fourth trophic level. So the direction that energy transfers is up the food chain. If I were to look at this as a food chain instead of a food web, the difference in a food chain versus a food web is a food web has branching and shows lots of connections, where even though it's simplified, it has a lot of organisms in it. And a food web on the other hand, a food chain on the other hand is just linear and is one portion of a food web. So I have here, oak tree makes acorns, which go to squirrel, which go to raccoon, which go to coyote. So clearly the tree is the producer. It's the autotroph in this. One of the things you need to think about is, of this tree, sure, there's acorns all over it, but only a portion of the tree's matter and a portion of the tree's energy is going to be transferred from the tree through the acorns to the squirrel. We say that 10% of the energy transfers along from one trophic level to another, and the other 90% is lost. So in this case, the tree loses that energy, uses some of it for respiration, some of the energy it harnesses from the sun, it puts into its own growth and into energy that it uses, and some of it is available to the next trophic level. Now, this squirrel, over the course of his life, is going to do a whole lot of things, and he's going to burn most of the energy he takes in, and he's going to burn that energy to do stuff. And when you do stuff and you lose energy due to metabolism, that energy comes off as heat. And then we would say 10% of the squirrel's energy is transferred on. Similarly, 10% transferred, 90% lost. And this is always 10% of the amount remaining. So if I was looking at the total amount of energy, let's say this was like, I don't know, a million, now let's go with 1,000 joules of energy that the tree harnessed, passed along to the squirrel, or the entire trophic level of the squirrel, not just this particular squirrel, would only be 100 joules. And then transferring to this trophic level, 10 joules, and then transferring to the highest trophic level is 1 joule. Okay, there are two laws of thermodynamics that we apply here. The first law of thermodynamics you've heard before, it's conservation of energy. Energy cannot be created or destroyed, just change from form to form. So our total amount of the energy in the system is constant. The second law of thermodynamics reads different ways depending on where you look at it. If you look at it in a chemistry or physics context, it says that the universe has a tendency toward entropy or disorder. What it means for us is that no conversion of energy or no transfer of energy is 100% efficient. This is applied a lot of different ways. If I light a candle under here and I try to transfer the energy from the candle to the can, it's not all going to go there. It's going to be dissipated. So this is applied in our food chains, as we're not able to transfer all of it from one trophic level to the next. It's also applied in the case of power plants, like literally like energy production or electricity production, that none of those systems can ever be 100% efficient too. So the way that the second law of thermodynamics is applicable to environmental science is in the transferring of energy never being 100% efficient. And a lot of times we look at what's generally referred to as the 10% rule. And it's not exactly 10, obviously, but the average from one trophic level to the next is about 10%. In aquatic systems, as opposed to terrestrial systems, it tends to be a little higher. You will also need to know 3 types of systems, thermodynamic systems. An open system, you can think of as like a pot of water over a flame. It's an awesome flame. And we can lose both matter and energy from the system. So we can have energy going in, we can have heat coming out, we can have matter coming out. That would be a typical open system. A closed system might be able to have something like light go in and maybe heat go out, but it's not going to exchange energy. I'm sorry, it's not going to exchange matter. So a closed system exchanges energy but not matter. The third type of system is an isolated system, which exchanges neither. Now, realistically, isolated systems don't exist. Nothing is going to be perfectly insulated. No light gets in, no heat gets out, no matter gets in, no matter gets out. Nothing is actually an isolated system because of the second law of thermodynamics, but we excuse me, frequently model things as an isolated system, even though it's not. Sometimes we assume over a short period of time that we didn't lose any energy from the system to the surroundings. It's a convenient assumption in solving some problems, but not necessarily a realistic one.